Okay, in the interest of keeping to time, I think we'll make a start on the webinar now. So just want to say good morning to everybody and thank you for attending our webinar today. It looks to be a very interesting session. So I just want to start by saying, giving a bit of an introduction. At Specific, our research is broad-ranging. It includes fundamental laboratory-based research, where future solutions for low-carbon technologies are investigated and developed. But it also includes combining novel and well-established technologies together to create whole building systems. So while getting the new solar cell technologies to work in lab conditions is an amazing and often groundbreaking feat, that's only half the story. So today we are joined by Professor Trystan Watson, our PV scale-up and processing lead, and Dr. Richard Lewis, a smart systems engineer and lead on all things electrical, electronic and controls related here at Specific. So firstly, Trystan is going to give us some insight into the current and emerging building integrated PV technologies. And then Richard will talk about some of the challenges in connecting building integrated PV into electrical systems within buildings. There will be time after the short presentations for a question and answer session. So please post any questions that you have in the Q&A box so that we can pick up at the end. Try and use the Q&A box if you can, please, because then we can capture them all properly. And then just to say, the recording will be available on our website in about a week or so, along with any answers to questions that we weren't able to answer today in the session. Okay, so that's enough for me. I will now hand over to Trystan to kick this off. Thank you, Trystan.
Thanks, Jo. It's really great to have the opportunity to present some of the things that we're working on and that we're interested in at Swansea. And it's an absolute pleasure to talk about how we might try and stop doing so much of this and just a little bit more of using this. And so what I hope to be able to get across, and there's quite a mixed audience today, so there's a good chance that I will not put anything of interest to anybody, but hopefully there's something in there for everybody. That's the aim. But what I want to talk about is some of the challenges that that we face in emerging photovoltaics, particularly as we look to work with people like Richard to take them on to the next level, because we have to be serious about that, even at the research and R&D scale. But it's been going for quite some time, PV, right from the Puebloan people from basing their houses on certain cliff surfaces, to the fact that PV in cars and boats has been around for a long time. And in fact, the first installation of building applied photovoltaics was actually over 100 years ago. Charles Fritz's roof of selenium. So we've come a long way, without a doubt, and we can now power boats and aeroplanes and cars and active buildings with PV. There's still quite a way to go. And I think if we think about the current projections, and these are meaningful projections, I think, despite them being projections, that we're at sort of the 500 gigawatt of cumulative installed capacity at the moment. But the reality is, if we're going to meet climate targets, that we're going to have to go a lot further. And so there's a role to play both in the incumbent industry of silicon, as well as the emerging solar cells that there are a number of us are working on, including those in the audience. Where are we in terms of solar PV technology status? Well, the majority of market maturity and penetration has been achieved by silicon solar cells. So for those of you that are perhaps not familiar with the technologies, those that you see on the roof, particularly in the UK, there's a very good chance that you're looking at a silicon wafer or of a monocrystalline or a polycrystalline nature. It's unlikely that you're looking at, potentially unlikely that you might be looking at cadmium telluride or SiC, although it is perfectly possible, as they have achieved market penetration. If we move further down the technology readiness level towards the R&D, that's where the new technologies, the emerging technologies currently are. They haven't quite made market entry, and I'll talk a little bit about what those technologies are as we move forward. But those that have achieved a module that you could buy, and that have had companies that produce them and have some market share within the global PV deployment, are monocrystalline, polycrystalline silicon, cadmium telluride, and copper indium gallium selenium, which is known as SiGs. So the incumbent technologies, as I said, if you're looking at a roof, the chances are you're looking at Nowadays, the chances are in 2020 that you're looking at a monocrystalline solar panel. They tend to take up now at least 80% of the annual production. Also worth talking about, where does that production come from? That's a relevant consideration in looking at emerging PV. It's mostly Asia. 70–80% comes from Asia, and a large part of that comes from China. So if you think about a solar cell at the moment, there's a good chance that it's a monocrystalline solar panel, and there's a good chance that it was made in China. So that's the current sort of state of solar research, solar PV at the moment. So looking at this graph in the top left, 2020, so some fairly modern numbers. Monocrystalline and multicrystalline, also known as polycrystalline silicon, are the major technologies. And the thin film market share, which represents cadmium telluride and CIGS, has changed from quite a considerable amount in the late 80s, 30% of a much smaller value, I should say, of course, right through to being a relatively small amount nowadays, but still a credible contributor. The difference between monocrystalline and polycrystalline is the way that it's made. They are slightly higher efficiency monocrystalline, but they're also more expensive to make because of the nature of the purity of the materials. But if you're looking at a roof, you're not looking at an emerging solar cell just yet. But certainly, silicon is not the only player in terms of what can be done via PV. So this is a well-known chart hosted by NREL, the National Renewable Energy Laboratory in the US. And you can access this independently if you're interested, and you can find out exactly where the best performing solar cells are now and where they were made. So for example, we've got perovskite solar cells, which I'm going to be talking about today, perovskite tandems, where you take perovskite and place it on top of an existing silicon solar cell. They're being developed now by companies such as Oxford PV, and you can understand where they are in comparison to the incumbent technologies of crystalline silicon. What's interesting about the NREL charts is that there's another version which is less well known, which is module efficiency, which is a very interesting take on understanding the evolution of technology over time. You can understand, how big can I make this device? Or how far is it towards being able to make something that might have some sort of large integration value? And the reality is, even perovskites of single junctions have been made at the sort of 800 to 6,000 square centimeters. We in Swansea are making that sort of lower end, small module, higher end submodule size. In fact, we make some in the small module area, and I'll talk about them in a minute. So these technologies really are emerging into a new area. Just to clarify what I mean by emerging solar cells, and you could possibly describe solar cells as having 3 generations: the first generation of silicon, the second generation of thin film, and then the third generation, which we might classify as perovskite, organic, dye-sensitized solar cells, or perhaps colloidal quantum dot. And there are other sort of inorganic materials that also can act as very nice photo-absorbing materials, which are also sort of emerging in that area. So that's what I talk about when I mean emerging, and we work in Swansea on perovskite and dye-sensitized and organic solar cells, and some of them do have market activity, so they do have startup companies. Oxford PV, for example, leading the way in perovskite, Powerroll looking to deposit perovskite on their substrates. There are a number of dye-sensitized solar cell companies, but it's not the sort of thing at the moment that you could go on to eBay or go on to Amazon and buy one of these technologies. It's not quite there yet. There are still some things that need to be worked through, but over the next year or the next few years, we're likely to start to see some level of market penetration. So new technologies, emerging technologies, have to be able to offer something new. So if they're going to challenge what is an established industry of 40 years heritage, then the reality is it needs to be different. And emerging solar cells do have something new to offer. Firstly, they can be semi-transparent. Yes, there are some existing technologies, amorphous silicon, that can achieve something at that level. They're flexible, which I think is also key. And they can be manufactured at relatively low capital and materials costs. Now, the silicon industry has a huge economy of scale in the sense that it's made in massive quantities. And a lot of those costs have been worked out. However, the entry-level cost of getting into the technology is still very high. The capital investment for purifying silicon is still quite high. So there is an opportunity for emerging technologies to bring that right down. And what these things offer, for example, and we're developing in Swansea, is the ability to do it via printing processes or ink deposition. So you take a liquid and you deposit it down onto a surface, be that surface metal or plastic or glass. And then it's flexible. So there are some design capabilities or deployment potential that an emerging solar cell can achieve. But of course, there is a pipeline to getting something which has just come out of the lab onto a building. Even before the work that Richard is going to present later, there has to be some considerations of how we do it. It's not a linear process, but I've attempted to present it like this. You go from hero device manufacture of tiny devices, you trial the processes, and then you have all of these more newer challenges in manufacturing optimization and interconnects and module lifetimes and stability that perhaps the physicists have been less involved in and the engineers are more involved in. And it's that hybrid relationship before you can start making large modules. And in Swansea, we do it via a roll-to-roll process on the left, as you can see, and on a sheet-to-sheet process. And perovskite, for example, lends itself to both of these types of fabrication. So there are benefits to roll-to-roll. There's a massive high throughput. You can link it with incumbent industries, for example, the steel industry, which deposits organic coatings via roll-to-roll, and then you can produce them via a really rapid, high-volume process. From sheet to sheet, generally is a lower capex. You can do it via screen printing, but typically is a batch process. So all of these considerations are relatively new in emerging solar cells. Everything is relatively new if you're developing a technology for the first time. So very briefly, in Swansea, then we develop a roll-to-roll perovskite, which requires us to print the liquid down and then heat it up and convert it to the perovskite. So there are challenges with regards to understanding the coating processes. We develop roll-to-roll devices of this nature at about 12 to 13%. So it is feasible to translate this new technology, this new emerging technology, onto a high volume production process. And there are still quite a lot of things that need to be addressed in terms of the coating parameters, the stability, the performance, the electrode contacts, but the feasibility of it is absolutely there. If we think about the sheet-to-sheet alternative, then we can screen print perovskite modules. So we can use a really low capital cost process to be able to produce modules of huge size. And so we've been trying to do that at Swansea to try and show that we can use low capital investment. So this is us developing an interconnect in a large area perovskite module, which we then hope and are in the process of transferring over to our building array measurement systems. And we can put the perovskite into those devices via automotive process. So the reason for showing some of these images is to say that in emerging technologies, often the method for making the devices doesn't exist yet. The factory doesn't exist yet. The manufacturing process doesn't exist yet. So you have to try and develop those processes as you go along. And perovskite is an ideal example of where dropping a liquid into a mesoporous structure, in this case, hasn't been done at scale in a particularly effective way for solar cells. So this is us developing our process. And as a last slide, we're now producing large area perovskite modules of what might be classified as a small module size. So it absolutely is feasible. And the question that comes next is, how do we engage that in the building? So the questions that Richard is going to deal with now are the questions that us as emerging solar cell PV scientists really have to start thinking about when we do our development. Thank you to my team, and thanks for giving us the opportunity to speak here. It's much appreciated.
Thanks, Trystan. Now we'll go over to Richard, who's going to talk about the next stage in this.
Hello, so welcome everyone. I'm Richard Lewis. I'm, as Joe mentioned, in the systems integration team and working with a team of people below me that interconnect systems and get them working from the novel research that Trystan has presented into something in reality on a real structure. Today, I'm just going to cover a few of the aspects that are involved, and by and large, BIPV is similar to normal PV, but there is a few intricacies that I'm going to cover. First of all, I'm going to describe some differences between building applied and building integrated PV. Slightly different, but they are both PV. BIPV types that are available, BIPV build program impacts and how they can impact the building as it's being constructed, design considerations, particularly for putting them onto buildings, string connections in accessible locations, which is the biggest driver of problems for BIPV, performance modeling and performance monitoring. So BIPV is the traditional framed, installed retrofit on a building, and it's fitting modules to existing surfaces. These can be roofs or walls more commonly now, once the construction of the building envelope has been completed. So usually the normal design and build process would happen, and the PV would just be a separate work package that's put on after the construction is mostly complete. BIPV, however, is actually integrated into the building fabric. So that's a fabric element that could be the roof or part of the structure of the walls. And that's materials incorporating solar modules. Now that's usually made by the manufacturer of the materials themselves, or through a subsequent process by a partner that would apply the PV to the structural element when it's put into the construction. The different types of BIPV, there's two key types really, which is rigid, and that's examples you see on the right there is glass panes for semi-transparent openings. So you do get some loss of light transmittance when you're obviously covering with a PV, because they are designed to absorb the daylight. But that's mostly where traditional glass would have been used. Other options there are roof tiles, mainly for domestic, not necessarily much for commercial, but examples such as the Tesla solar roof is coming on availability in America here soon, but that would be replacing the either slate or roof tiles that you'd have on a normal domestic premises. Semi-rigid is what we've used on a couple of our buildings, which you see an example of below on the bottom right, and that is curved around a profile during manufacturing and then installed onto the building, but it is slightly flexible when it's installed. However, that's once it's actually affixed to the building, it's in a static position and it won't move for its lifetime. So chemistries and their impacts on the construction elements. Crystalline silicon is traditionally is the most predominant in the market and can only curve along a faceted profile. So if you have the cells, they have a 100 to 200 millimeter flat section, and you'd have a faceted profile if you put that on a building. SIGs, which Trystan has mentioned, is usually thin films, and it's the default choice for flexible panels. So what you see here in the bottom right is actually a SIG cell adhered to a Tata steel standing seam roof panel. They have a medium bend radius. Obviously, you can't bend them too much because they'll stretch, but they are allowed, you can use them for truly curved profiles that you see in the picture below. And as Trystan was covering in the previous presentation there, emerging PVs such as perovskites have potentially much higher bending radius and could potentially be lighter. That will allow you to put them around poles and other structural elements that usually be steel frames and maybe external awnings and things like that. So what I'm primarily here to talk about is how it impacts the build program. BIPV panels, as they're part of the structural design, changing them after the construction has begun is a big problem. Normally with other PV that could go on the top of a roof, once the specification is made, there may be some alterations with the actual exact panel that ends up on the roof during the final stages of the build program. And that can usually be coped with because the framing system can accommodate different size panels, and the exact layout can be altered on site due to penetrations through the roof or extract or things like that. But BIPV, once it's designed for the building and shipped to site, it can't be modified. You can't cut into the middle of a pan section to add a feature of the building that's been delayed or added at a later date in the construction cycle. So that's a key thing that needs to be considered once the design is made for the structural component the BIPV is part of. It is no changes to that can be made. Lead time and the arrival to site is also critical. BIPV, as it's a higher integrated product and it's not just a normal structural component or a steel pan section, has to go through that additional process to be manufactured. And if there is a delay in that process, it's going to delay things like the roof being watertight or the structural integrity of the building being complete, ready for the next stage of the build program. One thing to consider is that BIPV on roof structures there will be a tendency to want to enclose that and the string connections. So in the actual wiring regulations in the UK, every connection should be accessible for inspection, testing and maintenance, and that can become a problem if you bury these connectors in the structure. So there are ways to mitigate that, and BIPV on glass roof panels allow connections to be accessible in removable frame components. So that's just a design detail that needs to be discussed with the manufacturers of the glass panes and the framing system. However, BIPV on steel cladding in enclosed roof voids present different challenges, and they must be permanent and maintenance free. And by default, a lot of the MC4 or EVO connectors are defined as maintenance free and tested and certified as such. But a lot of contractors may switch out for a different vendor of MC4 string connector, so that what cables coming out the back of the panel, joining them together in strings, they need to be specified and ensured that they are certified for their intended use, which is a permanent connection that are not accessible. And this needs to be really verified with the PV and roof installation contractors in the roof scenario to ensure that it's actually going to be as specified. So design considerations generally for layouts, you need to really allow for an acceptable loss of a certain percentage of the PV array before having to replace part of the roof. It's the last thing you want to do is to have to change the roof just because of a loss of some of the array because of connection failure or panel failure or mechanical damage. And the design of the PV strings then would be, it's an opportunity to design them in a slightly optimized ways for maybe at some point needing to do maintenance or replacement of part of a building structural component. Now in the picture you see here in the bottom right, here this is an actual layout of the active classroom building, and the strings in this building are actually designed to go up and down, so in the direction of the pans, and they are actually stringed in a couple of these pans. So the minimal amount of structural components that need to be removed from the roof is reduced to the easiest to do in post-construction. One other thing to consider is surface and ambient temperature within sealed roof voids if you are putting connectors in there. So we monitor in our buildings extensively, and this picture you see here is from the active classroom again. And to allow the string connections and the electrical connection to go in, a separate packed out roof void was added here with a OSB timber batten and another plywood layer. So this void between the two layers of the roof structure here is where the cabling runs go through. And temperatures in there can reach up to 50 degrees as it's part of the roof structure above the insulation of the building. So the connectors need to be suitable for the job they're doing and certified to ensure they're not cheap alternatives that could melt, which we have seen in other installations. Performance modeling is something that is slightly impacted by using BIPV panels. In the case of the standing seam that we have on our two buildings, there is a slightly high 30mm seam that goes along the roof panel. And in low light or low levels of sun inclination, this can actually cast a shadow over the edges of the PV module. And what that will cause is a slight loss of a few percent, but that all adds up. And that's something that needs to be considered if going through modeling, as they're not a standard flat panel. Also allow for the moving lack of free moving air around the panel. In a normal framing system, there would be a section of underneath that would be a void that might allow free cooling. However, in these situations, they're not. And then the last slide really is just performance monitoring. So system level monitoring should be by default. We monitor extensively everything in our buildings from the generation through to the demand. And it should really be part of the acceptance of the criteria for the installation being complete. We do speak to a number of partners who have had issues with monitoring not being put in place or being completely removed from the package and having to be an additional or retrospective snag that's gone on for quite a while. So that's something to really consider to make sure that's in there. And then string level monitoring is also something essential for integrated BIPV panels, because you want to be able to assess whether part of the array is failing and then mitigate that by maybe scheduling maintenance with a structural component replacement, which is rare, but it's something that you would need to establish whereabouts within the roof structure would need to be replaced in the case of roofs. And that's pretty much everything I have to say this morning. Thank you for the time, and I'll hand back to Joe.
Okay, thanks, Richard. Yeah, that was very interesting. Interesting to think about the temperature of the connections as well as just the actual PV, which, you know, something we might not necessarily have thought about. So yeah, that was interesting. Okay, so we don't have many questions so far in the Q&A box. We have just one at the moment. So somebody has asked, what would be the expected useful lifetime for a BIPV building panel? Now, I guess that depends on the type, but I'll leave it to you two to answer.
Go on, Rich. Okay,
so for our building, they're on Tata panels, so they are warranted for, I think, 40 years, unless I'm mistaken. And our PV panels carry a warranty of 25 years from the manufacturer we got.
I think there's a context in terms of emerging PV and how do you match the building. I think you have to plan to try and match the building guarantee, right? So even when we're working on emerging PV, we have to think about 20-25 year lifetime targets. What's interesting is that there are some few solar cells, for example, that were made in the 80s that are still functioning, that have gone way beyond that, some of the incumbent technologies. So what we have to do in the development stage is try and conform to the standards. Yeah, so understand what the ISO standards are for being able to keep our solar cells stable within, you know, the right frame of encapsulation, and also trying to do some external weathering. So there's lots of data that you can collect that will give you some confidence. And something like perovskite in the early stages was quite worrying about whether it would do it. Now we've moved on and we've done some of the technology developments. We are starting to see quite extensive tests and quite difficult tests being passed for perovskite cells and perovskite modules. So I think it's looking quite promising. And just as a brief comment, there are other technology markets that you can access before you get to building integrated to sort of try the technology, whether that's IoT or whether it's aerospace or whether it's some sort of canopy system that you can do where you can test it. So there are quite a few steps to get to which you need to explore to sort of give you confidence.
Thank you. Okay, so there's another question here. With the building integrated PV panels that we have on the roof of the active classroom, what happens at the end of life? Would it be a complete roof replacement? So I think some of this was covered. The thing about the PV that we've got in the classroom is you can remove some of the roof sheeting panels, so you wouldn't have to cover the entire roof. But Rich, did you just want to go back to that or talk about that slide where you showed the string layout of the active classroom roof?
Yeah, so as Joe's mentioned there, the modular, the way that the roof is put together with the pans means that they can be replaced. And it's not uncommon for a single roof pan to be replaced in a building due to mechanical damage or corrosion if it's been scratched during installation, and that's only been noticed in a few years. So it's very similar to the standard product replacement process. And with the PV, as Trystan has alluded to there, that even though the lifetime is guaranteed for a certain amount of time, the silicon panels there, they are, you know, a solid state device, and they have no moving parts. So usually the only thing you really get is a slight degradation or reduction in the performance. So they will work technically for as long as the building will stand, unless it's hundreds of years. But the only impact you'll see is a loss of generation of 20% or so after 20 years.
I think that's actually a really good point that we don't tend to talk about that much, is that often when we're talking about degradation, we're not talking about a binary situation where it either works or doesn't. I mean, that's bad. That's a catastrophic failure. We're often talking about a reduction in performance. And at that, you've got to balance it with, you know, better use of technologies elsewhere within the building. So I think that's a very valid point, actually, that we're not always talking about catastrophic failure.
Yeah. And I think this is a really important point when you come to look at whole life costing, because we had a life cycle cost analysis of our active classroom, and that actually showed that over a 60-year period, the PV roof would be entirely replaced every, I think it was 3 or 4 times during that time, which of course would be very expensive and disruptive and not great from an embodied carbon point of view. but in reality, that wouldn't actually be the case. It would continue to be working. So even if it was reduced capacity. So I think there's more research needed in those areas, definitely. And there's another question here, are they recyclable? And that's interesting, especially when you're integrating the technology into another fabric. I believe the BIPV product that we used on the classroom and office, the steel is completely recyclable. So I'm not sure what happens with the thin film element of that. Do you know any more about that, Rich?
So the panel itself is bonded with an adhesive which can be removed, so that the panel can be reused effectively. Recycling is still something that's being looked at for these nature of these panel SIGs and anything with a polymer sheet over the top of it, because they're not glass. So that's something that's still in process, and to be honest, it's a few years down the line before any would need to be recycled at that stage.
For emerging PV, then the answer is that it's part of the research process. So whereas it's absolutely not something that we're delaying consideration about until we're further forward. So there are research groups in Swansea, for example, led by Matthew Davis, which is looking at the sort of sustainability element, the recyclability element, the reuse and remanufacture of materials as well. So even in the design process, we think about critical raw materials, we think about earth abundancy, we think about, co-mining of materials with other materials. All of that cradle to grave process has come into the considerations already. So we're trying to avoid making any, deal breaker mistakes that might mean that we get to a certain amount of production and then we could go no further. So we're having those considerations already.
Thank you. Another question here, what are the efficiencies of the integrated PV compared to silicon panels?
So that depends on the type. As I mentioned, the couple of types there, the rigid PV is effectively standard silicon, monocrystalline or polycrystalline silicon in just a different form factor. So the actual efficiencies are very similar. Active area might be reduced slightly because of the framing requirements, but the actual cell efficiency is the same. For SIGs, which is the semi-rigid or flexible that we use on our buildings, their efficiency is obviously lower than the monocrystalline, but they are comparable to other SIG cells. So generally, the vast majority of them are comparable to their exact static solid framed equivalents.
Yeah, and I think it can make a difference, with the SIGs that we've used on our classroom, you can cover the entire area, you don't need walkways between, you can walk on the walls. So that makes a difference as well, I think, in terms of overall efficiency. Okay, so how do we retrofit roof integrated systems like the GSE mounted system compared to BIPV and BAPV? Are there issues for connectors, strings as with BIPV? Yeah,
so the GSE mounting system is the same as any other PV installation or electrical installation. It's the connectors it's a design consideration for the electrical. So yes, in every installation, the connectors need to be accessible unless they are certified to be maintenance free. So that is purely a manufacturer and vendor specific design criteria. And saving money on the connectors will mean, potential headaches in the future in removing part of the roof if the string fails because of the connector.
Yeah, thank you. Okay, so we've heard that there are difficulties and challenges with BIPV roofs versus traditional panels, but what are the advantages of this approach versus use of traditional modules? Now, I can say from an architectural point of view, it's very nice to have PV integrated into the building. Any other views from either of you, Rich or Trist?
Perhaps I can comment on the benefit of emerging PV such as perovskite. I think there's a conversation to be had about whether you want to go head to head with the incumbent mega industry of silicon manufacture. If you do, you need to be competitive without a doubt on stability and lifetime and cost. There is, of course, the opportunity of augmenting the existing technology, and I think that's something that we probably should make clear, is that perovskite can be applied on top of the incumbent technology to make it better. So these are the concept of tandem solar cells. So there's single junction and then there's multi-junction. In fact, the junctions can go up to 3 and sometimes 4 different junctions. So you can take perovskite, for example. You can actually do it with CIGS and cadmium and other types of second generation, and you can make them a double layered structure. So we can take an incumbent industry which is finding it difficult to go up incrementally in terms of its performance and give them a genuine performance boost. So that is where perovskite will come into the market, I think, initially. Will be making existing silicon solar cells better. Before then, we might see the evolution of single junction perovskite solar cells.
Thank you. I was just wondering how you go about connecting printable PV, the printed PV. How do you go about making electrical connections for that? Have we thought about that yet?
So these are conversations that are ongoing actually as we speak. So over the last couple of weeks, I mean, this is where the connectivity between a research team, which, you know, in the early stages of lab device, smearing silver contacts, I mean, lots of labs do that, to an engineering team that do not want that, that want a strict system of connections. So, for example, we make modules that work of large area perovskite, and we've got to now develop the way in which we connect those modules up. And the questions that we're asking is, do we borrow from the incumbent industry and learn from their ideas of being able to add connectors, or do we need to do more? It's, for example, printing silver anywhere near perovskite is generally a bad idea. So whereas you might screen print silver onto a silicon solar cell, you certainly can't do that for perovskite. So we have to think differently, both at the pre-encapsulated module scale and the connections that come into it as well. And where do we locate them? So those conversations are ongoing, and they're starting to emerge now. It seems that it is going to be feasible for us to be able to produce some robust and rigid electrical connections to the modules. There's no game changers there, but it's a conversation going on at the moment.
Thank you. Did you have anything to add to that, Rich, in terms of how you'd go about it?
No, as Trystan said there, it's an engineering challenge once the chemistry is solved. And yeah, we're looking into it in our team as well.
Excellent. Thank you. Right, I'm not seeing any more questions here. I just want to remind everybody again that this recording will be made available and that will be sent out in the next week or so. It'll also be made available on our website along with the question and answers that we've had. So are there any other questions that anybody would like to ask? I'm not seeing any. In that case, I think maybe we will end the webinar, and I just thank everybody for attending and for your questions, and hope you all enjoyed. Thank you all.
Thanks.